Hello, and welcome to Chapter 14, Inference for Counts. I'm not going to lie, this is probably my favorite chapter in our study of statistics. I have a little bit of affinity for the chi-square test, and yes, that is how you pronounce it. It's based on the Greek letter chi, which looks like just a fancy-looking X. So if you want, you can go watch an introduction to this chapter that'll remind you of how this connects to Stat 1. And we're going to learn a bunch of different uses of the chi distribution. So be thinking, oh, I know the normal distribution, I know the student t distribution. We're going to add to that list by adding the chi. And then I'm going to show you the different ways we can use the chi distribution. So although it's not noted here in the title, we're also going to learn the difference, or I don't even want to use the word difference. I'm going to say the two proportion test in here. Yep, that went well. Okay, well, you get the idea. It won't let me write it. Two proportion test. Let's get it. Okay, so the first type of test we're going to learn is what's called the goodness of fit test. So basically, the idea is that chi is really used for categorical variables. And the first thing we're going to look at is we're going to look at categorical counts and ask ourselves, oh, for these different groups, or if I compare to two different groups, do they have the same distribution? So I'm going to have different categories within my categorical variable and look at the counts for those and compare them to another variable with the same categories and compare those counts and say, oh, are these the same distribution? Or if you want to think about it another way, how good is the fit? How similar are these two? Does the model match? And this is usually used for historical data, comparing like groups from previous historical records to current groups. So if I looked at like Northwood University's current student, I don't know, let's say student makeup, so when I look at like freshman, sophomore, junior, senior, graduate, compared to maybe even 10 years ago, you could ask yourselves, is the distribution still the same? Is it about the same makeup as it was previously? So that's one thing the goodness of fit test can do. All right. So here's an example that can kind of help you, and this should look a little bit familiar. This is the stock market data. Again, I know there's only so many free databases out there in the world, so bear with me here. One of the things you might ask yourself is, oh, are there certain days where the stock market tends to trend up more than others? So these are the counts for up days for certain days of the week, and then the count for the distribution for a whole trading day. So as you look at this, on the left, my table is from the bull market time period. That was from the 1982 to 1986 region we looked at a couple of lessons ago, and then compared to an entire year. So, or I think this is actually a little bit more than a year. I think this is a decade, because you know, we're looking at the up days compared to like all trading days considerably. So you might notice a couple things. So look at the percent days up for each of these for the different days of the week. So if you look at the sample, it looks like, you know, Monday's a little low compared to everybody else, but Monday is also a little low compared to everybody else on the distribution of all trading days. And interestingly enough, we're high on Wednesdays, and on the other distribution, we're not high on Wednesdays, but we're low again on Fridays. So, you know, it looks like they might be different, but this difference might be caused by random chance. So we should be using testing, hypothesis testing, or the otherwise, in this case, goodness of fit testing, to see, hey, you know, is this caused by random chance and it's really a probable thing? You know, these are actually distributed the same way. Or is it the fact that, you know, they are super different? So you might be asking yourself, is Friday off large enough to be considered a recommendable planner? Or is Monday off enough? No. We get the idea. Okay. So the first thing we're going to look at is what are the assumptions for this test, and then we're going to apply it. So here's your assumptions. The goodness of fit test can only be done on counted data or data of counts. This is what we would consider categorical data, data that we have counted the number of. So I'm hoping you've looked at our previous results in Chapter 13 and said, oh la la, that appears to be quantitative only. This is definitely the categorical versions of that. The next thing we need independence. The idea is that our counts should not depend on each other. If they are dependent, you actually need a different type of testing to do this. And we also want randomization. We always want this because it can guarantee that I have a good representative sample, and well, you should expect to see randomization on like every single test, pretty much ever. Anyway. Here's our last assumption. We need a decent sample size. So the sample size condition is it has to be large enough for the method to work, and really that condition that it has to be large enough is that for each of your individual cells, so for each of our individual categorical combinations, we have at least 5. The problem is if it gets smaller than that, it becomes very difficult for the chi to be able to tell whether or not you, sorry, what am I thinking of? Chi can't tell the difference once it's super small. So it can't tell the difference between like a 1 and a 4, which is super weird. So thinking back to my example of looking at the different classes at Northwood, freshman, sophomore, junior, senior, graduate, you would have to have at least five students in every category. So as you look at that, that automatically means that your sample has to have at least 25 people in it. But even then, 25 might not be enough, because it could be that you have like 1 person in graduate and like 10 people in another group and so on and so forth. But you need to have at least 5 of each. So sometimes with this, you have to sample larger than what you might expect. So here's what the chi model looks like. Now the chi is a little unusual, but it looks a little bit, I'm sorry, I'm going to sneeze, so I'm going to pause. Okay. The chi looks a little bit like the standard deviation but without the root, so it kind of looks like a variance. And here's how it kind of behaves like a variance. So we take the observed values, so the ones we see within our data from what we gathered in our sample, and compare them to the values that we expect, square that, so how far off I am, how much is my error, squared, and then compared to how large I'm supposed to be anyway. So this is really, if you think about it as an error, this is a percent error because I'm comparing it to how big my data is. You know, the idea is that your error might be $1,000, but if you're dealing with millions of dollars, that's a really tiny error. So we take size in account. And the last thing it does is it adds it up across all your possible categorical combinations. This means that chi accumulates. So you might be off in one cell just a little bit, and then when you look at another combination of things that makes a cell, you're going to end up with something that's much, much smaller, and then like there's one of them that's big. So it just keeps getting bigger. So if all of the cells are small, as in your error is not that big, then your chi looks small. If one of them is big, it makes everybody look big. And this is why I like to call chi the one of these things is not like the other test, because it very quickly detects a single cell that has more error than everybody else. So how do you calculate that? Well, this thing's long. I'm not going to lie to you. I don't like to do the chi by hand. You totally can do it by hand. But we're going to probably use technology to do this because it is much quicker and much more effective. So here's how you would do this. And I'm going to do the example from earlier when it came to looking at the stock market by hand on the next couple pages, but and talk to you a little bit about how that was calculated. But I don't recommend you do it by hand because it's a little bit of a messy disaster and it gets ugly real quick depending on how many categories you've got. So the first thing you have to do is you find the expected values. And then, you calculate the residual, observed minus expected, square those, and then divide, and then add them all up, and that makes your chi. Then you find your degrees of freedom, which is just one less than the number of cells that you have. And then you calculate the chi-squared with that, which is the probability that you got, that score or worse on the chi distribution. So you should be thinking of the chi-squared statistic behaves exactly like a test statistic. And then you calculate the probability that you got it or something worse depending on your alternative hypothesis. And then your distribution depends on your degrees of freedom. So this is going to determine what your chi looks like. And I'm going to show you some graphs of some chi's too. Well, I can't do that in this video, unfortunately, so it'll happen in a different one. Whee! I have lots of examples of this one. I got a little overboard because I kind of love chi. I'm so biased, it's sad. Okay, so here's how you would do the number of up days in the stock market. Oh my gosh, look at this. So if you're thinking, how did I calculate these expected values? Sorry for the long pause. Welcome to allergy season. I just sneezed again. So if you're looking at this and wondering, oh my gosh, how did she calculate these values? So the first thing I did is I took my observed values and I added up the number of days that were there. If you remember, this totals to 1,110. And then I took this value and multiplied by how much the expected ones were from the very, very second slide, where it was the percentages. And I took those and I multiplied them by 1,110, and that came up with these numbers. So there's how those came. So these are the values I should expect if the distribution from what we saw on the overall all stock market days was applied to something that had this sample size. And this is actually how you do calculations for the expected values of chi. Although most statistical software will not handle doing percentages for your goodness of fit test, it'll only handle counts, just so you're warned. Minitab is okay with using percent, so I didn't actually have to do this if I didn't want to do it by hand. I wouldn't have to calculate all these values over here. I could have gotten away with in Minitab just putting in the percents, which is kind of nice. Anyway, so let's get down to business. So I got to subtract the Mondays from each other, square it, and divide by the expecteds, so on and so forth. So you notice you're going to have to do these fractions, like there's going to be 5 of these gross huge fractions, and then you got to add them all up and come up with your chi. Great. And then I got to find the probability that I got this score or worse. Here's the thing. Chi's a little bit weird with the or worse. I'm out of space. Let's go to the next slide. Okay, so now let's calculate the p-value for the stock market up days example. As you're looking at this distribution down below, I'm hoping you notice that there's a p-value being calculated. Hey, probability time. This part of the symbol is just saying, oh, it's chi-squared. And then right here you have a 4. Why is there a 4 there? Oh my gosh. And how do I know that this is a greater than? So here's the thing. Chi, since it's accumulating, it's only going to be possibly positive. Chi is always a right-tailed test. It's always a greater than test. So it takes some of the guesswork out of this, or if you've had a hard time with hypotheses and coming up with p-values, it's always a greater than. So it's always this way. Always. No ifs, ands, or buts or anything else. This 4 down here is actually the degrees of freedom. I'm noting here that my distribution is different for every single chi and for every single degrees of freedom. So every single chi looks different from the previous chi, and I'm going to get into that a little bit after I do an example. But this would be, since I have 5 days of the week, my degrees of freedom would be 5 minus 1 or 4. So I'm noting here that I'm using the degrees of freedom for chi-square distribution to do this calculation. And I did this using technology. So I did it using Minitab actually, and I rounded a little bit. You can do this using tables. There is a table in the back of your book that does this for fun facts. So if you want, you can use that value. But other than that, we're good to go. So since my p-value is like almost 60%, that's pretty huge, I should definitely not be rejecting. I got something really, really likely. So what we'd say then is that, okay, it appears I have no evidence that they're distributed differently. They appear to be behaving the same way. And that's exactly what I have down below in blue for a formal conclusion. We would say that it's not distributed differently. In fact, it's exactly what we should expect on each day of the week. At a major credit card bank, the percentage of people who historically apply for silver, gold, platinum cards are at the rates of 60%, 30%, and 10% respectively. In a recent sample of customers, 110 applied for silver, 55 applied for gold, and 35 applied for platinum. Is this evidence to suggest the percentages have changed? So we're asking, compared to how it previously goes, is this different? This is a very typical goodness of fit question. Is this different from how it was previously? So we're going to say, what kind of test do you conduct? I kind of just gave that away. What do you expect? What's the expected values? Find the test statistic and the p-value, and then we're going to state our conclusion. Let's get it. All right, I need to quit saying that. So down below, I'm like, oh yeah, you should totally use the goodness of fit test because we're comparing two distributions to each other for the same set of categories. As you look at this, I hope you are noticing that these are counts. So I'm good to go, and they're categories. So clearly this is a categorical variable. I absolutely should be using the goodness of fit test and be using the chi-squared. Okay, so how did I come up with the expected values? Well, on this table up above, if you notice, I have the observed. So this was just the stuff from our sample. If you total this, it's 200 individuals. And then look up above, 60% historically apply for silver. So I just took 60% times, or sorry, 60% of 200, which is exactly 120. And then I did 30% of 200, and that gives me 60. And then I did 10% of 200, and that gives me 10. So that's how I'm coming up with the expecteds there. Minitab will let you put in the percents. You don't have to do this for Minitab, but if you're going to do this by hand, you absolutely do have to come up with the expecteds, and they do have to be counts, just so you know. All right, so here is how you would do the test statistic down below. So notice I've got my observed for my sample minus my expected squared divided by the expecteds, and if you do just these three groups, you can add them all up and come with 12.5. Now, as you look at this, I'm hoping you're seeing that, oh, okay, so if I only have three groups, it's not so bad to do this as it would be if I had, like, 20. Which totally can happen to you. So 3, not so bad. We can totally hang with 3. 3 is very, very doable. So the last thing we need to note is we need to find the p-value. So I need to go ahead and calculate the degrees of freedom. And then I noticed here I said that I use table X, which is a table in the back of your book. If you do not have your book, you have access to the ebook online, and you can get it on there. And I'll post one for you just as well. I also had a good internal giggle about how the chi distribution is on table X. Chi kind of looks like an X. Okay, maybe nobody cares. Anyway, the p-value you get here is 0.0019. Super tiny. Wonder what we're going to do. You already know what we're going to do. You've been doing this long enough. Rejection? Oh my gosh, it's so tiny. So what this is going to allow us to say is that yes, they are distributed differently. Clearly there's evidence that the customers are not applying at the same rate they had been previously with the traditional proportions for the distribution. Something has changed over time. Gee, I wonder what. Let's take a look at the chi. So here are two different chi's distributions with two different degrees of freedom. So I'm hoping you notice that the chi gets more skewed the higher degrees of freedom you have, and it does start to look kind of like a squished normal, but that's about as normal as it gets. It doesn't really get normal, and that's exactly why we use a different distribution for chi. And he also, when for you have small degrees of freedom, has what we call a heavy tail. One tail is much more thicker and skewed than the other, and the other one's elongated and takes forever to get small. So there's one way to look at this. The expected value or mean of the distribution is always the degrees of freedom that you see present. So, as you look at this, 5 is about the area equality on the degrees of freedom 5 one, and the same thing is true for the 9 one. So just a little bit to one side or the other of the mode due to its skewness that it has. So that's what chi looks like. So when I say that chi is different for every single degrees of freedom, I mean it. And so for a single value that you might be looking at the probability on, if you put in the wrong degrees of freedom, yeah, a little bit of problem. I also noted down here that I was doing the degrees of freedom -2 version of this. That's going to come up later. Just maybe let go of that for now. With the goodness of fit, you do number of cells -1. For some of the other ones we're going to do, it's different. There you go. I explained it. Whew. All right. So one of the things since you can do, since chi is always a one-sided test, is you can look at the standardized residuals for this. And that's to tell you how far off the expecteds are from the observed. And this is kind of useful if you're trying to pick out who's the unusual measurement, or if you think there's 1 or 2 days a week that are 1 or 2 cell values that are a little bit different from each other. So chi might tell you, oh, these look different, but it's not going to tell you who's different. And that's kind of a downside. So one of the ways you can solve that problem is to look at the standardized residuals. We'll see what they look like for our days of the week example for up days on the stock trading example. So here you go. So in particular, I look at these and notice that, ooh, we got some ones that are much further than the others from each other. So the most unusual measurement would be Monday, because its standardized measure is the farthest from 0. So one of the things you could do is you could look at the largest Monday, and although it seems most unusual, it's just barely 1 standard deviation away from the mean. 68, 95, 99.7 rule tells you that's not that interesting. If it was like -3, I'd be like, whoa, super crazy times. Monday appears to be the one that's weird. But then again, if Monday was that weird compared to everybody else and that different, it would be statistically significantly different. And therefore, we'd probably be rejecting our null. And remember, in this example, we did not. Okay, let's look at the other chi-square test. Well, there's two more, but another? That's the word I should have used. Too late now. So, I know I say in Chapter 2, Pew Research. Okay, if you had me, you saw this before. If you didn't have me, you didn't see this data before. So we're going to look at what's called the test of homogeneity. If you've never heard the word homogeneity before, homo means same, gene means shape. So we're looking for, are these the same shape? So this data was looking at people's responses to their social networking patterns in the modern society, and I'm hoping you look at this and you're like, oh, on the total column, my samples were all about the same size per country, and then on the other, sorry, this is the total on the right side of the screen. I'm looking at the totals for every single country. If I look down, the total values for yes, no, and not applicable, so I'm looking at the bottom of the table, they are clearly not the same values. So overall, it appears that some of these selections are more likely than others. All right. So you might ask yourself, oh, is social network usage or non-usage, choice non-usage, different among different countries? And hopefully we can answer that question. We're asking, are these different? Or are they all the same? Do they all have the same distribution amongst the three groups? So this is clearly categorical data. As I look at this, you need to keep in mind that I am looking at responses per country and asking, are these two related to each other, or does it look different amongst each country? I'm going to look at a graph to try to determine some instinct on this. Gahahaha! I hate stacked bar graphs sometimes. So here's an easy way to read this. Look at the far left and look at the purple stuff. The nose. Does that distribution always look the same? I'm giving you pause. This is awkward. Nope. All right, now look at the far left and look at the green. It's like there's a distribution. For the not applicables, are those the same? Nope. And even then still, you can look at the thickness of the pink bars and compare them to each other and say, oh, well, Germany and Egypt appear to be about the same size, but they look different from Russia, US, and Britain because those ones all look about the same size. But even then, Britain seems to be a bit bigger than everybody else. I wonder if this is enough to be different overall, or is it just natural sample variation? Maybe I should look at this again or take a different sample and see if that changes anything. Then the only way we're going to be able to figure out, is it caused by natural variation or is it statistically significantly different, is to actually do some statistics. Okay, what we're looking at is what's called the chi-square test for homogeneity. Homogeneity is all about testing, do these groups all look the same? And then the alternative is, one of these things is not like the other. So the unfortunate side effect of doing the test for homogeneity is you're not going to be able to tell who's different. It's just at least one of them must be. So the null hypothesis for this, so the null hypothesis for this is that the distributions are the same for all groups. So for my specific example that we're going to be looking at next is, oh, the amount of yes, no's, and non-applicables is the same for all countries. So I'm really testing the countries and their percentages across the other variable, the similarity amongst them, which is a little bit strange. Yeah. And like I said, really the test is going to be able to tell you, is one of them looking different? Or is many of them looking different? I can't really tell. It's just one of these things is not like the other. So here's what the expected counts looks like. The expecteds are not easy to calculate. So you might be wondering, how on earth did I come up with these values? And I'm going to show you how to get just one of them. They're all done similarly from this. Basically, you're going to use the conditional distributions for every single cell to figure out the total count. So the conditional distribution for Britain, no. Sorry, I was trying to circle that and that didn't happen at all. Would have been to do the total for Britain divided by the total overall. And then the total for no divided by the total overall. So one of the weird things about this is you know, you're doing essentially a multiplication, but you want counts. So you fudge it a little and turn it into counts out of everyone instead of a probability. So what this ends up looking like is I take my column total for that cell times the row total for that cell, and then divide by the total. And that will give you your expected counts. So following along to make sure we understand, let's do a second one. So let's say I wanted to do the Russian yes. To calculate this one, I would use the row 1010, my 0 didn't show up, sorry about that, times the column 2175, and then divide by the total 5039. And that would come up with that value. If you don't believe me, you can calculate those real quick, and there's how you get them. So again, this is one of those things where Minitab will do this for you in 2 seconds. You do not have to know how to do this by hand. In case you were wondering where they came from, there you go. Conditional counts. Let's look at the assumptions needed to do the test for homogeneity. So the first thing is we need to have counted data. We need this all to be independent, nothing new here. We need randomness, and then we need to make sure that we have at least 5 in every single cell. So that's that same it can't be too small idea. Still true even for the test for homogeneity. This is also going to be true for our last test, the test for association. All right, so, you know, we're going to take and figure out all our components by doing the expecteds subtracted from the originals, squaring them, and then adding them all up. Now, one of the weirder things about the chi-square test for homogeneity is that its degrees of freedom is calculated differently from the previous. So I'm hoping you notice down here that the degrees of freedom for the homogeneity, that is so dark. Regret. So much regret. Don't worry, I've got an eraser. Sorry you had to listen to that. Light blue. Nope. Nothing but regret happening today. Yellow. Okay, sorry, I guess I'm limited to yellow. You basically do the degrees of freedom for the rows and the degrees of freedom for the columns and then multiply them together. So for my countries example, I had 5 countries and then 3 responses. So that would have been a 5 minus 1 times a 3 minus 1, which would come out as 4 times 2. So that would be 8 for my degrees of freedom for that previous example on the previous slide. Let's do a real example all the way through. So we're going to do homogeneity. So this is looking at the credit card application data again. So the market researcher in this example for the credit cards wants to know if the distribution for applications is the same for 3 different mailing groups. So this is testing to see which of these seems to bring in more customers. So they have different mailing groups and they probably have different setups for each of these. And so she does 200 randoms from every single group, counts the number of applications from each credit card type that they're receiving, and then they're going to ask things like, hey, well, you know, what type of test do you conduct? Gee, I wonder. Hint, hint, wink, wink. What are the expected values? And then we're going to calculate the test statistic and the p-value and actually draw a conclusion. So looking at this table, I'm going to do my row and column totals, multiply, divide by 600. And it shouldn't be too surprising that if all of the mailings had the same total size, as in this column all being the same, that when you do this, all of your columns look the same since you're using this value for your column every single time. So you might look at this and be like, really? Are all my rows supposed to be the same for the expecteds? Yup, they are. Okay, so we're asking, are these distributed differently? And that's why this is a test for homogeneity. And additionally, I'm hoping you notice that since this has more than one and I'm not comparing historical values, this is clearly not a goodness of fit. All right, let's do our test statistic. So to calculate the test statistic, I'm going to take all of those cells, just in case you forgot, there are 9 of them. Do all those differences, square, divide, and then add all of them together. Whew, and you get 2.7860. Couple things, since the cell that we were looking at previously was a 9 by 9, when you go to do your degrees of freedom, that would be a 3 minus 1, 9 by 9. It's a 3 by 3. Whew. Minus the 3 minus 1. So that's going to be a 2 times 2, or a degrees of freedom of 4. So if you calculate the p-value, it's bigger than 10%. Like, I don't even remember what it is, and clearly I didn't write it down because I'm awesome at this. Ooh, self-deprecation. Here we go again. So, it's huge. It's way bigger than it should be. And that's not too surprising because look how small this chi is. You know, big chi makes small things because it's a right-tailed test. Anyway, so we're going to fail to reject the null. We're going to not be able to say really much about this other than there's insufficient evidence to suggest that the distributions are different for the 3 mailings. They appear to be producing the same amount of customers for each. So mailing out different things didn't make a difference. Darn. Weirdly, I'm going to do the test for 2 proportions. I'm doing this in order for what your book does so I don't confuse you. I really think this belongs at the beginning. Let's go for it. Whew. So when we have counts in a 2x2 table, you really don't need to do a chi-square test for homogeneity. What you're really looking at is just a simple t-test with sample p-values, so comparing 2 p's. Let me show you what I mean. So here's some Super Bowl stuff from Chapter 2, looking at males and females, and whether they wanted to watch the Super Bowl because they have the game or the commercials. So what's interesting about this is as you look at it, you might ask yourself, oh, is the distribution for males and females different? Well, you look at it and you're like, well, yeah, physically they are different. I mean, there's, more females watching the Super Bowl for the commercials than there are for the males. Okay. Whatever. But there are also fewer people in the commercial section than there are in the game section. And even then still, could have been caused by random chance. Doesn't mean it's statistically significant. Only one way to find out. That's to do a test. So you might be thinking, chi-square test of homogeneity. Hey! So you'll totally do this and end up with a chi of 37.26. That's huge, in case you were wondering. With the degrees of freedom of 1. Which means on average, your distribution has an average of 1. So you get a p-value that's super tiny. And then you conclude, hey, men and women, they seem to watch for a different reason on the Super Bowl. So you can go through and look at just the percent of women who watch the Super Bowl for the commercials and find that it's 43.47%, sorry, 75. And look at the percentage of men who watch just for the commercials, 22.19. And then just do a z-test for the difference. So be thinking this is harkening back to sorry. Oh, come on. This is going back to, I'm pausing, hold on. So this is harkening back to the idea back where we were looking at Chapter 13 and comparing like 2 means. You can do the same thing with 2 proportions and ask yourself, is, P1 equal to P2, or is like P1 greater than P2? And here I'm looking at like a null and alternative. Woohoo! Or you could do a difference test and ask things like, oh, well, is P1 minus P2 positive? Stuff like that. Or is P1 minus P2 0? Same idea, still works. Here's the thing though, the test you're doing this on is just, well, it's a t distribution or a z, it's not doing the chi. So if you do a test of 2 proportions, here is your standard error for the 2. Basically you're averaging across the 2 different proportions, and then when you go to do the confidence interval, the estimator is just the difference of the 2 of them, and then the margin of error is the standard error times z star or t star depending on which one you're doing. I know I wrote z star on here, I really should have written either. This still works, it's still just a test of 2 proportions, it's just with proportions and not means. So here's a summary of those 2 together, and in particular then you can estimate the difference between your 2 proportions. Minitab will do this as well. So I'm going to take my men and women Super Bowl survey, put in their information, and come up with the fact that, oh, holy crap, this is always positive, isn't it? Ha! So as you're looking at this, you can say that we're about 95% confident that between 14.82% and 28.30% more women than men watch the Super Bowl for just the commercials. Not only is there a difference, but it's definitely always positive. I think that's more informative than just doing chi and being like, oh, they're different. not really gonna say how. They just are fun, fun, fun. This is far superior in my mind, and I'm hoping you see the use for this as well. Now, we're going to look at one last use of the chi-square test and the chi-square distribution, and it's a little strange, but it's also like awesome. This is where, when I was a student, I fell in love with chi and realized just how amazing chi was and helpful it was. I don't know if you remember Stat 1, but there was one part of Stat 1 that always made me upset, and that was, how the heck do we find independence? We kept on having that assumption everywhere. Assume the following are independent. Assume this is independent. Assume these are independent. And then there was one and only one definition of independent that we had. And that was, oh, well, if I look at the probability of A given B, knowing B told me nothing, and I'll just get A. And if I looked at the probability of B given A, knowing A tells us nothing about B, and then you got B. That was the only way to tell if A and B were independent. Well, if you didn't know how to calculate any of those probabilities, you were hosed. There was nothing you could do. Erg. So the downside to that was there was no real good test for independence. One of the assumptions for the chi-square test is that they're independent. Because of that, and because of how chi is constructed, you can actually use it to test for independence. Let's look at an example. So I don't know how you feel about aging. I'm not going to tell you how old I am. Most of you are very young. You might have an inkling that appearance and how old someone is might be related to each other. Specifically, as you look at the appearance rating that appears on the left of this column, not at all important, average important, extremely important, and then the age groups, you might notice something. Pay attention particularly to the 4 or lower column rows, as you look down the columns. As you look at the younger people who are, and the just barely teenagers group, aka 13 and 19, there is pretty heavy on the higher values end, like 4 and above, super big, 4 and below, well, sorry, below 4, not so much. And then start looking down that column. You know, those 60-year-olds, they'll hump anything, evidently. Because notice that the number of people who found the appearance extremely important is much lower than it was before. So one of the things you might say is like, oh yeah, it appears this tapers off over time, or this changes. So you might ask yourself, are these related? Knowing someone's age, can you predict how important they find appearance? And also knowing somebody's average rating for importance of appearance, can you predict their age? Are they related or are they independent? And this is something chi can actually do. So by asking, are they independent, this is the same thing as asking, oh, is there a relationship between them? And then the other version of this is, are they associated? So one warning, if you read other textbooks, this is also called the chi-square test for association, not just independence. So we're going to look at a stacked bar graph again. I'm hoping you notice some trends here, like the fact that as people age, the width of the bars that are extremely important, so along the top, get smaller over time. Yeah. And the middle bars get wider, and so do the lower bars. So it appears that if you look at this, I would say age and relationship look pretty not independent, because as you increase one, the other one changes. So they're looking not independent. Let's see if that's true. Just because I suspect this is true doesn't mean that it's not caused by random chance. It could be. And we need to detect whether or not it's statistically significant. So, couple warnings. This is mechanically the same as doing the test for homogeneity. They are coming out as exactly the same calculations. It's just your conclusions and your hypotheses and what you're trying to detect are different. So what's the homogeneity test really doing? Looking at one variable measured across multiple populations, aka appearance measured across country. Independence is asking, if I look at 2 variables in a single population, not multiple populations, are they related? So these are 2 different questions, but mechanically, when you're calculating chi, look the same. So it's important that you know the difference between the 2 of them, and detecting the difference in the variables that allows you to tell which of these tests that you are doing. Otherwise, you'll be making incorrect conclusions. Okay, so we're really asking, are they independent, not are these groups distributed the same way? So be careful. Let's look at assumptions and conditions, because I just warned you to be careful. Alrighty. So we need counted data still. We need to have the expected cell count be at least 5. You got to have enough data to be able to figure that out. The 5 does that. Needs to be random. And then the counts need to be independent for each other. Or you need to at least suspect they're independent, and you'll know whether or not they are in a little bit. The counts being independent is a matter of, I didn't overcount anybody, nobody appears in multiple categories kind of thing. So when I look at one group, I don't find any of those individuals in another group, so I'm not overcounting. The counts need to be independent. That's to say, is if I had like one person who was 30 who said, oh, well, I think my importance rating is a 4, I can't use that person again in a 3 if they change their mind. I only get to put them in one place. All right, so here's the expecteds. Please don't do these by hand. I'm hoping you notice there is 7, 1, 2, 3, 4, 5, 6. Holy crap, you would have to do this 42 times. Let technology do this. So then if you take the expected minus observed, square them, divide by the expected, and add them all up, all 42 of them, you get 170. I'm hoping you recognize that that's enormous. Big chi-square means there's a big difference. There's clearly a difference here. Up above, I noted that your degrees of freedom is a 30, so I'm like, oh, it's a big chi-square, but it's also a big degrees of freedom, so it's spread out a little bit more. Oh, sorry, I couldn't help that one. The p-value for this comes out very, very tiny. So what do we conclude? Hey, well, with a low p-value, we're going to reject that null. And then we're going to say, oh, well, it appears that attitudes on personal appearance are not independent of age. It appears these two are related, or it appears these two are associated. I'm going to write those on here. So again, we'd say these two or you could say age and appearance rating are associated. Okay, that or looks bad. So I got lazy with this one, but they are related, or these are related. So these are associated with each other. Association is something you might harken back to correlation, which correlation and linear regression was a way for you to detect whether or not two, come on brain, two quantitative variables were related. Are these two related? Let's check the correlation. Ah, is the correlation significant? Yes. Okay, cool. These two appear to be related. Same idea, but with categorical variables. Hey, are these two related? Yep, they're associated. Cool. It appears these two are related. I'm repeating myself. That's a little obnoxious. You get the idea. Association, still the same idea. Let's do an example. Okay, so automobile manufacturing. This appears to you automotive individuals. The Consumer Reports uses surveys to measure reliability about automobiles. Annually, they release their survey results about problems that consumers have had with their vehicles in the past 12 months and the origin manufacturer. Is consumer satisfaction related to country of origin? This is an interesting question in my mind. Sorry that I picked this one based on selfish interests. So we're going to state our hypotheses, then we're going to give the test statistic and look at the p-value and use it to state your conclusion. Well, I gave the p-value because this data was huge and there was no way I was fitting it on here. So this is good practice for you on your null and alternative hypotheses for this and your test statistic. So what I would suggest you do is actually pause this, write down what you think the null and alternative are going to be, and then you can use when I advance to check to see if you're right. Ready? 1, 2, 3, here I go. All right, so here's what you would say for your null hypothesis and your alternative. We're looking for country of origin and consumer satisfaction. Your consumers are all from different populations, different countries. Your different countries are all different countries. Clearly, this is a test of association or independence, not a test of homogeneity, because of my two variables, neither of them is from the same population. So here we go. My null hypothesis is that the rate of problems is independent of the manufacturer's origin. I assume independence. I prove whether or not it is true. So my alternative is going to be that they're actually not independent. So be thinking Is independent is saying no relationship. Not independent is saying there is a relationship. These two are related. They appear to not be independent of each other. So be careful. If you're going to use relationship and association, it's actually the opposite of the independence, guys. Okay, so, oh God, I listed some of the test statistic stuff for you, and you have no idea where it came from because I didn't list my data. Hey, there it is! I hate myself. I'm not re-recording this because it takes like 3 hours to get done. Okay, so given the p-value, let's state our conclusion. Well, that p-value is pretty big. It's bigger than 5%. It's bigger than 10%. We're going to go ahead and we're going to fail to reject. So there's not enough evidence to conclude that there is an association between vehicle problems and the country of origin, which is good news for auto manufacturers who might care about which country their automobiles are getting manufactured in. So if you're worried about cost, yeah, you can go ahead and move it to a different country. Good times. Okay. So back to the appearance and age example. When we rejected the null hypothesis that the variables were independent. So you might ask yourself, like, how different two age groups appear to, rate, appearance. In which case you can use our previous example of looking at two proportions to construct some confidence intervals. Here's how you would do that. So you're going to take the appearance groups of 6 and 7 and look at teens versus 30-year-olds and construct those two percentages. And then you can do the difference of their two proportions. Sorry, I said percentages earlier, I meant proportions. And then you can form the standard errors, and I'm using the 95% here, so I'm using 1.96 for my test statistic. And there you go. You'll come up with the interval. So you'd be able to say that there's a statistical significant difference. And we can actually see that the difference might be as small as 1.8%, but it might be as large as 8.7%. And we can decide how to allocate different things to keep this up. So I think this is really interesting demographically. So one of the reasons why I think you see so many more advertisements with appearance and altered images in teen magazines versus someone like my age range. However, there are still magazines out there like Cosmo and Maxim that are just chock full of appearance-based advertising for some of the older age groups. I don't know anything really about the like AARP group and what their magazines might look like. I'm going to go ask my mom. You go do the same. Or whichever parent you happen to have that is around that age range. If your parents are in that age range, yours might not be. Oh no. Okay, let's not think about this. Ask your favorite 60-year-old, whoever that is. Maybe don't go ask strangers. We're at summary time, so I'm clearly losing my mind. So what can go wrong? Don't use chi on non-categorical count stuff. You shouldn't be using it on anything other than categorical things. Oh. Beware that chi doesn't really work well for stuff that's super small. And don't say that one variable depends on the other. We say not independent. Being dependent is actually something totally different, so be careful. Well, it's not totally different, but it's different than being not independent. What have we learned? Well, we learned 3 chi's today. Whew, exhaustion. Okay, we learned the good is to fit, the test for homogeneity, or how do these look, and then the squared, the test for independence. Don't forget, calculating expecteds is kind of a disaster. Let technology help you. Woohoo! Be careful because for each of these tests, they have different null and alternative hypotheses. You don't want to be picking the wrong one. Be careful interpreting the chi-square test, even though you can say things like these two appear to be different, or at least one of these groups is distributed differently. You don't necessarily know which group or by how much. For that, you will need to use other testing and things like the difference in two proportions. When it comes to comparing two proportions, make sure you set up your null and alternative hypothesis and understand how to do those. I guess the one thing to offer is that when it comes to comparing groups and things like that, more detail is always better. So if you want to do more than 2 groups, you can, or you can compare groups of groups and their differences as well. We'll see this a little bit more when you do your projects. Woo-hoo! Okay, that was lame. Have a good day.